Welcome back to Physics 152 Online. You'll notice thus far in our discussion of Gauss's law that we've talked only about charge distributions on insulators. And that's because, to keep things simple, if we charge up an object, we'd like to study the electric field in its vicinity, assuming that the charges don't move around. Conductors are a little bit more complicated to work with because they are materials through which charges can easily move, with essentially no need to do work on them. So if we charge up a conductor, the charge immediately can flow on that surface until it reaches an equilibrium configuration. Also, conductors have inside them lots of mobile charges of their own. So for example, a chunk of aluminum has electrons inside of it, some of which can readily move around throughout the sample, and that changes the kinds of properties that that object is going to have when it's charged up. So what we want to do is use Gauss's law to find the electric field in the vicinity of conductors, especially those that have an excess charge on them, but we've got to review the properties of conductors when they are in electrostatic equilibrium. So if you do deposit charge on a conductor, it only takes a very short time for the charges to flow around and reach positions where the forces on them are equal to zero. That's equilibrium. And after this happens, the conductor has special properties that make it very different from an insulator. There are four properties that we want to talk about, and Gauss's law is an essential part of figuring out these properties. First of all, if you have a conductor, it's a solid conductor, then the interior part of it, the solid part, has the property that the electric field is equal to zero. How do we know that? Well, we said the charges are in equilibrium, which means they feel zero net force. Well, if you have a conductor, it's got free electrons in it. The electrons are charged particles. So if there were an electric field inside the sample where the electrons are free to move, then those electrons would feel a force, and they would not be in equilibrium. So we have the situation, assuming that you can have an equilibrium configuration. That equilibrium configuration must be characterized by having a zero electric field in the interior of the conductor, in the solid part. Secondly, if you have a conductor that's not neutral, but has an excess charge, we've somehow charged it up by transferring additional charge to it, any excess charge resides on the surface. And Gauss's law shows us how we can deduce this property. Imagine a solid slab of conductor here that has this sort of ellipsoidal type of shape, and inside the conductor we know, if it's in equilibrium, that E is equal to zero. We assume we have put some charge on this conductor and we want to find out where it is. So what we can do is draw a Gaussian surface that would be, remember, a Gaussian surface, even though we draw it here with a dotted line, it really represents a volume. So it's a closed surface inside of which we can relate the electric field to the charge enclosed. So we make the Gaussian surface contour to just barely be inside the surface of the conductor itself. And then we simply apply Gauss's law. Integral E dot dA, that's on that closed surface, equals the charge enclosed by that surface over epsilon zero. Alright, so if E is equal to zero inside the conductor, then by virtue of that, the left-hand side, the flux integral, is equal to zero because E is equal to zero. And if that's true, then by necessity, the charge that's enclosed by that surface is equal to zero. Now, of course, there are positive and negative charges inside that region, but they balance out and give us a net total charge of zero. And we can make that Gaussian surface as close as we want to the surface of the conductor itself. So in that limit, this tells us that any excess charge that there is can't be in the interior and has to sit on the surface. So that's an important property of a conductor. Now, just outside the surface, right, if a charged conductor has if a conductor has charge on its surface, then there will be an electric field outside, because a positive charge would feel a force due to that surface charge distribution. And we can show, again using Gauss's law, that this electric field just outside the conductor has a very simple form. How do we do that? Imagine here that we have a block of a conducting material. We've seen this kind of geometry before. And imagine that we deposit on a surface charge density sigma. And it's easy to get uniform surface charge densities on conductors because when you deposit charge on it, the charges want to flow in such a way that they get as far away from each other as possible and spread out uniformly. So there's easily going to be this uniform surface charge density. Remember that sigma represents charge per unit area. And that means that the electric field perpendicular to that surface, the electric field is perpendicular to that surface if it's a very, very large surface. So we are going to choose, in order to find an expression for the electric field just outside that surface, we'll choose a Gaussian cylinder like we did in a previous problem. And that cylinder is such that it's got a cross-sectional area A, which is the intersection of that Gaussian cylinder with the top surface of this conductor. Now apply Gauss's law for that Gaussian cylinder. We know, of course, a cylinder has a top surface, it's got a bottom surface, and it's got a side surface that's curved that wraps around. So the flux integral has three parts to it. The right-hand side, Q enclosed over epsilon 0. The bottom surface now gives us a zero contribution because the bottom surface is inside the conductor. And we've already deduced that the electric field down there inside the conductor is zero. So the middle integral goes away. The side integral also goes away for a different reason, because if we were to draw in the dA vector, the dA vector for the side would go radially outward away from the axis of the cylinder, and that's perpendicular to the electric field direction. So E dot dA is then zero, leaving only the flux integral for the top surface, and that top surface, as long as it's a surface that's parallel to the surface of the conductor, we can expect that the electric field is parallel to dA and that the electric field is uniform on that top surface. So E dot dA becomes E times dA, and then the E comes outside the integral because that field is uniform. So when we solve for E, it's easy because this integral is just now the area. Adding up the area dA on the top surface of the conductor just gives us the surface area, and the right-hand side with the enclosed charge is just sigma times A, because that charge sits on this little circle that has cross-sectional area A. So the surface charge per unit area times the area gives you the total charge. And finally, E is equal to sigma over epsilon 0. And the direction we already deduced by just thinking about which way a positive charge that sits just outside the surface would feel a force. So very simple result there. And here is an example for an irregularly shaped charged conductor. Here's an example of what the electric field just outside would look like. You would have field lines that would be perpendicular to the surface everywhere. Notice that the charge distribution is a little different on the surface. It's different at points of high curvature than it is at flatter points where there's low curvature. And we see that points where there's high curvature, which could be sharp points on that surface if they existed, that's where the charge density is highest. And so a consequence of this is that when you rub your feet against a carpet in the wintertime and then touch a conducting object, a spark will often jump from you to the conducting object or from the conducting object to you, and it usually happens at a very sharp point on the surface because the charge density is highest there, which means the electric field is highest at that kind of a point. One last thing. We'll now use Gauss's law in a very powerful way to answer a question that's not trivial at all. It's a really difficult problem and gives an example that, at least to me, is a little bit counterintuitive. So let me set the stage and then work the problem out. A point charge plus 5q sits at the center of a conducting spherical shell with inner radius A and outer radius B. We put charge on the shell so that the shell, the conductor, has a net charge of minus 3q. Find the charge density on the inner and outer surfaces of the conductor. So here's the cross-sectional view. This is a conducting spherical shell. It's empty on the inside, which is where the point charge is located, but we know if there's any excess charge on a conductor, it has to reside at the surface. But this is a special kind of conductor because it's got an outer surface, but it also has an inner surface. So that total charge of negative 3q, some could be on the outside, some could be on the inside. And that's our goal. Figure out how much charge is on the outside and inside, and then express that as the charge density, which would be the charge per unit area on those two surfaces. So how do we do this? Well, we know that the total charge on the conducting shell is the sum of the Q that's on the inside, Q inner, plus the charge that's on the outside, Q outer. And we know the sum of that is minus 3q. But that doesn't solve the problem for us. We want to be able to find these two charges separately. right? And this equation alone only tells us what the sum is. So the strategy in using Gauss's law to solve a problem like this is to choose a Gaussian surface that lies in a region where one of these charges will be inside of it, will be enclosed by it, but the other one will be outside of it. And that will allow us to apply Gauss's law and solve for one of those charges. And of course, if we can solve for either Q inner or Q outer, we can get the other one from this equation here that tells us the sum. And so once you see this strategy executed once or twice, it's pretty easy to follow it. What you do is you pick a Gaussian sphere so that the radius is in between the value of A and B, which means the Gaussian sphere has its surface that sits in the solid region of this conductor. And now we apply Gauss's law, and you'll see what happens on the right-hand side, which is really important. The left-hand side, when you pick a Gaussian surface that's inside a conductor, the left-hand side is trivial because the electric field is equal to 0. So E dot dA becomes 0 in one easy step. The charge that's enclosed by this surface includes two terms. There's the plus 5Q, the point charge, and then there's whatever the charge is on the inner surface, Q inner. So Q inner plus 5Q is the total charge enclosed. And the sum of that, those two, has to be 0 because the epsilon 0 doesn't come into play at all. So what we have found through this careful application of Gauss's law is Q inner is equal and opposite to the point charge at the center, minus 5Q. Right? So Q outer, so if we know Q inner, sigma Q inner, which is the charge per unit area on that inner surface, is minus 5Q over the inner surface area, 4 pi A squared. Now what about Q outer? We now go to the sum. We know the sum of the two is negative 3Q, and so the only way that that can happen is if Q outer is plus 2Q, which gives the surface charge density on the outer part of the sphere as 2Q over 4 pi. That should say B squared. That's a typo on my part. So it should be plus 2Q over 4 pi B squared, or then Q over 2 pi B squared as the final answer. Sorry about that. Notice, though, that this answer is a little bit counterintuitive because one might think, right? One might think that if you had a charge at the center, that all of the charge that's on the outer sphere would flow to the inside, right? That you would have, if the total charge is negative 3Q, that you would have negative 3Q on the inside because it would be attracted to the plus 5Q. In fact, something more subtle is going on. You actually get more than that amount of negative charge attracted to the inner surface, and the reason is that that's the way you can distribute the charge on the inner surface so that the electric field in the conductor, as it has to be, has the value of 0. And then the excess charge is on the outer surface. So you stare at that a little bit, take a look at that, and see if you can make sense out of it. But the answer, the charge distribution that you end up with, where you have negative 5Q on the inner surface and plus 2Q on the outer surface, is not something that I would have guessed before solving the problem, which shows the power of Gauss's law. So we'll do some more of these in class, and that's where I will see you next.